bear is the same in each case. So once again, the bear could be moving at a constant velocity, and the box is the one that's being accelerated upward by a constant non-gravitational force, like, for example, a rocket engine accelerating it. Or the box could be moving at a constant velocity, which may be zero, and the bear is being accelerated downward by a constant gravitational force. So those are the two things that could be happening, and the observed behavior would be the same in each case. Now, suppose you're still in the sealed box, being accelerated through space by a rocket at a equal to 9.8 meters per second squared. So you're accelerated by a rocket, and your acceleration is 9.8 meters per second squared. You grab the flashlight you keep on the bedside table and shine a beam of light perpendicular to the acceleration vector. Since the box is accelerating upward, the path of the light will appear to you to be bent downward toward the floor, as the floor of the box accelerates upward to meet the photons. So again, since the box is accelerating upward, the path of light will appear to you to be bent downward toward the floor, as the floor of the box accelerates upward to meet the photons. However, thanks to the equivalence principle, we can replace the accelerated box with a stationary box, experiencing a constant gravitational acceleration. Since there's no way to distinguish between these two cases, we're led to the conclusion that the path of the photons will be curved in the presence of a gravitational field. Gravity affects photons, Einstein concluded, even though they have no mass. Wow. And why is that? Because, spoiler alert, gravity bends space-time. So, and since photons will move in space-time, photons can get curved due to gravity, okay? So gravity affects photons, Einstein concluded, even though they have no mass. So having mass is not necessarily needed if you want to be affected by gravity. Contemplating the curved path of the photons, Einstein had another insight. A fundamental principle of optics is Fermat's principle, which states that light travels between 2 points along a path that minimizes the travel time. Wow. Wow, 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 wow. In a vacuum where the speed of light is constant, this translates into the requirement that light takes the shortest path between 2 points. In Euclidean space, the shortest distance between 2 points is a straight line. In the presence of gravity, however, the path taken by light in a vacuum is a curved line. This led Einstein to conclude that space is actually non-Euclidean. It's not flat and Euclidean, but it may be, just maybe, non-Euclidean. The presence of mass in Einstein's view causes space to be curved. More broadly, in the theory of general relativity, mass and energy, which Newton thought of as very different things, are interchangeable via the equation E equals mc squared. Moreover, space and time, which Newton thought of as very different things, form a four-dimensional space-time. A more complete summary of Einstein's viewpoint, then, is that the presence of mass energy causes space-time to be curved. This gives us a third way of thinking about the motion of the teddy bear in the box. No forces are acting on the bear. It is simply following a geodesic in curved space-time. The word geodesic in this context is shorthand for the shortest distance between 2 points. In general, computing the curvature of space-time is a complicated problem. Since the distribution of mass and energy is inhomogeneous on small scales, the curvature of space and time is also inhomogeneous, with strong curvature near black holes and neutron stars and weak curvature in intergalactic voids.